In the problem lunchtime name recall, we are trying to identify the names of n colleagues by giving them burgers or salads to eat for lunches. On each day, we can choose a subset of colleagues to get a burger, and the remaining colleagues shall get a salad. By observing who eats a burger and who eats a salad, we can correspond the colleagues' names to the actual persons and gain information about their names. Let's say we have three colleagues named A, B, and C. We don't know who is A, who is B, or who is C. On the first day, we order one burger for colleague A. And by observing who eats a burger, we know who has name A. On the second day, let's say we can order two burgers. Let's give them to A and B. So the colleague who eats a salad on the first day and a burger on the second day will be B, and the remaining colleague shall be C. Consider burgers to be values 1 and salads to be values 0, then we essentially have a binary matrix and we can reorder the values in each row. Our goal is to maximize the number of columns that are distinct from all other columns. The problem can be viewed as a process of partitioning. We start with an initial partition of a single group of size n. For each group of size g, we can decide to place k burgers into it and split it into two smaller groups of sizes k and g minus k. Consider sample 2. We start with a single group of size 16. On the first day, we have 6 burgers, so we can split this group into two smaller groups of sizes 6 and 10. On the second day, we have 8 burgers, so we place 2 burgers into the first group and 6 burgers into the second group, and got 4 smaller groups. On the third day, we can further split these 4 groups into these 8 groups, and we will get 5 groups of size 1. The number of groups that have size 1 is our optimization goal. So how many ways we can split 30 elements into 1 to 30 groups if the groups are only distinguishable by their sizes? There are only 5,604 ways, which is A30 listed in a well-known sequence. And this value can also be computed by simple dynamic programming. Since it is not big, we can probably track all the ways to create the partitions. Say, each partition P is represented by a sorted list of its group sizes. Then on some day, we can pick an existing partition P and decide how to distribute the burgers we have today into the groups of P. For each group in P, we can decide how many burgers to place in this group in order to split it. So we can model our state to be the partition to be split and the partition we already split. And of course, we track the number of burgers we have left. And this state is for each day. So for each state, we can consider the first group, let's say it has size g. We can enumerate k, the number of burgers we place into this first group, and we will remove group g from the partition to be split, and we will get two smaller groups in the partition we have already split. And of course, the number of burgers left is decreased by k. So we need to estimate how big the state space is. Let's say p2 split times p split, the value of this is s. And of course, we have s here. And we multiply this value, multiply s, by the number of burgers. This gives us the total number of states, which is ns. For each state, we need to enumerate the choices of k. So this has a linear cost in terms of n. And also, after we make a split, we need to maintain the sorted list of group sizes. This is also linear in terms of n. So our total cost is n to the third times s for each day, and we can multiply this by m, the number of days. This is our total complexity. To roughly estimate s, we can say s equals the sum of ai times a n minus I, where I is even. I is even because the number of groups in P split is always even. This is about 300k, and the total is about 8 times 10 to the 10th. This seems a bit slow, but because it's a loose bound, so it gives us the intuition that the actual algorithm may run faster than that. So let's do a more precise analysis. Where do we overestimate? So we see that the enumeration of k depends on the size of the first group and also how many burgers we have left. And how many burgers we have left cannot exceed the total group sizes in the partition to be split. And of course, the cost to maintain the sorted group list depends on how many groups we have so far. If we run a program to take those into account precisely, we will see that the total cost on each day, represented by n to the third times s, is actually only 5.6 times 10 to the seventh. This is a much better estimate. And if we multiply this by m equals 10, we will get our total cost as 5 times 6 times 10 to the eighth, and it is feasible. There are at least two ways to further reduce the constant factor in this algorithm. So we see that the number of burgers AI is equivalent to n minus AI, and we can simply take the smaller value between these two and reduce the constant factor by a factor of 2. And we will also be able to terminate early when we find the maximum possible answer n. Although these will speed up the solution, neither of them is required to solve the problem.